Okay. Well, we continue with lecture first, then when people comes more, then we can resume the discussion yesterday. The tutorial for the assignment question. Okay. Okay, let's continue first. So yesterday, the last theorem we proved was the Uryshon lemma. So the content of Uryshon lemma is if you have a T1 space, it's normal if and only if for every disjoint set AB in X such that there exists a continuous map F from X to the closed interval 0, 1 with FA equals 0 and FB equals to 1. Okay. So we use the normality of X to build a dense subset of open set. Okay, dense subset of open set such that we can define F on these based on this dense subset of open set in X. Okay. Hello. Is it better? Okay. So inspired by this Uryshon lemma here, we will define that what is separation by a continuous function means. Okay, when can you separate two things by a continuous function? So we'll define that if you have two subsets in your topological space and there's this continuous function, okay, from X to 0, 1 such that FA equals to 0 and FB equals to 1, and I think we should put a set notation to talk about set equalities here. We will say that A and B can be separated by a continuous function. So in this case, the Uryshon lemma will turn into an equivalent statement that a T1 space is normal if and only if any two disjoint closed set can be separated by a continuous function. So one might think that can we use the proof of Uryshon lemma on regularity or not? Okay. What's about normality? Normality is about separating two disjoint closed sets. Can we use the same proof? Instead of A, we replace the closed set A with a point. Can or not? Okay. In general, we can't. Okay. In general, we can't. So this prompts us to more separation axiom here. Okay. So first, we will define that a space is functionally Hausdorff if for every distinct point in X, okay, there exists a continuous function X to 0, 1 such that Fx equals 0 and Fy equals to 1. Okay, so what's the difference between Hausdorff and this functioning Hausdorff? So Hausdorff meaning you need to exist two disjoint open set. Okay, but what is functioning Hausdorff? You use this function, okay, to kind of differentiate the 2 points. Okay, so we call this a functioning Hausdorff, and we'll call a space T 3.5. Okay, what's T 3.5 here? So we'll call that a space is T 3.5 if for every closed set A in X and every point not in A that exists a continuous function X from 0 to 1 such that, do you want to guess what property this is to hold? So FA has to be 0 and Fx is 1. Okay, T 3.5. And we'll say that a space is completely regular if it is T 3.5 and T1. Okay, so you see, we put T 3.5. What are we suggesting here? This T 3.5 is somehow in between T4 and T3. Okay, T4 and T3. So there are very easy propositions that you can prove. So you can prove that a normal, so you can prove that normal implies complete regularity, and complete regularity will imply regularity. So you can prove this. So we have new implications put inside the long one. You still remember the long implication we get last time? We have what? Normal implies regular, regular implies T2, T2 implies T1, T1 implies T0. So now we slip this 3.5 in the middle of normal and regular. Okay, no? Okay, so this proof will leave as an exercise. It's very easy exercise. Please do it. This is a very good test whether you know the definition or not. And I will put it into my lecture notes. And also you can check that complete regularity is actually both hereditary and productive. Okay, so it is hereditary and productive. One example you can see is the lower limit R, but you take the product of lower limit is completely regular but not normal. This is a one example that you cannot go back to show that completely regular doesn't imply normal. Okay. Yeah. And so these are the consequence of Uryshon lemma. Any questions so far about this new separation axiom here? Any question? I think I didn't say anything useful, so that shouldn't be any question unless you think of something else. Do you have any question that you want to ask about this new separation? Doesn't mean by T4 doesn't imply T3.5. T3.5. The example is it? I mean T is T3.5. So the proposition says normal imply regular here. Yeah, implies. T4 implies T3.5. T3.5 don't implies T4. Be careful a bit. But so do we use T1 in our proof or not? Do we use T1 in our proof? T1 in our proof. Let me think again. So T4, did we use oh we didn't use, wait. I think we did not. Because in this case, yeah, because T3.5 need uh, points and closer. So you want the point to be close so that you can apply the reason there. Yeah, you need it. So when you want to go to close set to point, then you need it. Yeah. So whether you need it or not, this will like as a bit in this proof here. Okay, so please write down the proof. And then I think I will write down detail about this example here. Okay. So why we do a recent lemma here? Because we are going to do a recent metrization here. So this is about whether we can metrize a space or not. So what does it mean by metrizing a space? Okay. So this is something that back home quite worry about whether we can have distance between 2 points or not in a topological space. This is about that thing, that concept. Okay, whether you can put distance on your topological space or not. Okay, so a topological space is said to be metrizable. So meaning you can put matrix on it. Okay, so how to put matrix on it? So you should put your matrix such that this is the matrix that induce your topology. What does it mean by induce the topology? What does it mean by induce the topology? How to give? The question is, what do you mean by expand? Expand what? Yes. So in matrix, you can naturally look at the open ball. So this open ball is precisely the open set in your topology. If not precisely, then must be generated maybe. Okay. So the thing that you declare open in your topological space, you can somehow obtain it from the matrix, open ball in your matrix. So the notion of open in matrix coincide with the open in topology. Okay, no? Okay, so we will say that it induce. So subsequently, so we can give a new definition of a metric space. So do you want to try and give us the meaning of metric space using what we have now as a metric space? We paraphrase this definition. First, as a mathematics student, you learn to paraphrase, right? So can you paraphrase the definition of metric space? is a topological space that is induced by a matrix, or you will use the word that we have just defined is a metrizable space, right? Metrizable space X together with a specific metric D that gives the topology. Okay. And somehow you go from topological space back to metric space. Yeah. But for matrix space, you still need the matrix function. So you need to have metric on it. If you just said generate by open ball is a set. I can forget about the metric. Does that make sense? So I need to put the metric back. So that's why here says that with a specific metric. So you need the metric distance. If you just talk about open ball defined by this metric, I can just single out the open ball. I can forget how to compute the metric. I just take the open ball out. I just look at the set of open ball. I can even forget how this open ball comes from. So now you cannot forget. You need to have the D function put it back into this metric space. So metric space is defined by what? What's the definition of metric space? Set with metric that satisfy some axiom. So you need to have a set and a matrix. Okay. So you need to tell me what matrix I need to put on this metric space. Exactly the matrix that give you the topology. Okay. Yeah. So metrizable space here already imply that this space is a topological space. Okay. So it says that matrix space is a topological space that is metrizable. Okay. Yeah. So you cannot simply metrizable it. You need to metrizable such that it induces the original topology. Okay. So this is the content of this statement here. So a proposition is you can easily prove the metric induced topology is Kostov and first countable. Okay, this proposition only need 2 lines of explanation. Okay, let's start with Leongyuan. Why is it a matrix induced topology is Kostov? They just need 1 line argument here. What is Kostov? Open disjoint what? How do you think about Kostov? There are 2 points. What can you do about 2 points there? You can separate them using 2 open sets. Okay. So if you already have a metric on this topology, can you separate any 2 points or not? So how? You say can, then you must tell me how. Correct or not? Cannot just say. Uh, okay, you said they exist, so fine for me. You said exist or? Hmm. Good. Yes, that's right. That's right. Right? Very easy argument, right? Go back to like first few weeks again. Although we use so many like advanced term, it's still the same concept. Okay, no. Okay, next one. First countable. Right? Gary. Sorry? Sorry. Open. Yeah, open. Good. Yes, that's right. The important thing is open. Right? Gary, what is the first countable? What's first countable? Countable basis at each point. Yes. So you need to come up with a countable basis. How do you come up with a countable basis at each point? There's one natural choice, right? Yeah, that's all. That's right. Yeah. Okay, because of the Archimedes property, you can find for every real number, there's a natural number that's greater than the real number. Then you take the inverse. Okay, yeah. So the argument here is really what we did before in the metric space. Okay, we just put things together now. Okay, we try to put all the things together. Good. Fine. Okay. Well, last time we skipped one example. I said we will prove in tutorial. So I decided I think we will do it together for this example here. So every regular space with a countable basis is normal. Okay, because later we will need it for a recent metrization lemma. I think it's good to see how we put these two conditions together to get normal. So what is the countable basis and a space with a countable basis? It's a second countable space. Okay. So it says so another in equivalently it says that every second countable regular space is normal. So what's the difference between regular and normal? Uh-huh. Which one is which one? Okay. So now I tell you that I can separate a closed set and the point. Now I want to advance to separate two closed set. Okay. But with an extra condition here. I know that my basis is for the topology is countable. So how are we gonna do this? Let me see. 1, 2, 3, 4. Okay, not too long. So to this end, what do you need to start with? You have to separate two set, right? So you need to start with two closed set in X. Okay, so let's do it. So prove that be a regular space with a countable basis V. Okay. And then start with A and B such that they are disjoint closed subset of X. Okay. So what you know is for every X in A that exists an open UX in X such that UX intercept B should be empty. This is just a regularity. Moreover, yesterday we proved equivalent characterization for T3 and T4, right? Moreover, we can find a smaller open set such that the closure is living inside UX. Okay, we can go smaller a bit. So using regularity. Okay, we can choose open Bx in X such that the Vx closure is living in Ux. Okay. Yeah. So now we have this basis property, right? So for each Ux here, okay, we can choose Bx inside my basis such that Bx is in Vx. So this is the basis property here. Okay, there is an element in the basis such that Vx is living in Vx. Okay, so what are we gonna do next? Okay, so you can imagine that I did this for all the point in my set A. Okay, I did it for all the point in my set A. But how many choices of Bx you can take? Only countably many. Even though maybe your point is uncountable, even is uncountable, but maybe you might pick overlapping choice, or not, because there are only countable many things you can pick from. Okay, so by choosing such a basis, element for each x in A, by the second countable property, we can really at most construct a countable covering. Okay, countable covering of A by open set whose closure does not intersect B. Okay, it does not intersect B. So our point here is we need to stay far away from. So let's denote it. Denote the covering by UN, say, okay, because it's countable. Okay, we can label it enumerable. So the same thing here. Okay, so similarly, what we can do is we also can do the same for our B. Okay, so we can choose a countable collection WN of open set covering B. So it's the same thing such that Wn bar is disjoint from A. Okay, disjoint from A. Do the same thing to B. But can you just take the union of these two or not? Okay, so the question is, can we just take the union of these two? So clearly, if you look at U as a union of UN, this thing surely contains A, and then if you take the union of WN, surely contains B. But the union of all this have to be disjoint or not. Okay, you know that all the WN is disjoint from A, all the UN is disjoint from B. Okay, but how about these two? Are they disjoint or not? So another question is, if you are disjoint from B, can you be disjoint from something that contains B or not? Must it necessarily disjoint? Might not be, right? Okay, correct. Does it make sense? Very easy concept, right? Semi-detached house. Your house is disjoint from your neighbor, but your house is not disjoint from your neighbor's house. So what's the trick we need to apply here? Unfortunately, these two things might not be disjoint. Okay. These two sets might not be disjoint。大家知道什么叫 semi-detached house 吗？知道什么是曼杜利屋吗？永远怎么？哎，非常好，有什么关系？什么是曼杜利屋？先回答先。我们要在一起哦。什么叫做两个家在一起？Yeah，共用一个墙壁，共用一个墙壁。对呀，就是共用一个墙壁。所以这边的想法是，UN 是 A 的家，WN 是 B 的家，对不对？它 contain 它嘛。我跟你讲，UN 跟 B intersection 是零，肯定吗？不可能，你的邻居忽然间跑来你家嘛。A 跟 WN intersection 也是零哦，你也不会跑去邻居家，对不对？但是你们两个家会不会可能有 intersection？有，可能没有，可能有。OK，所以不一定，might not be this one。OK 吗？OK 啊，so we have to settle this problem here. So how do we settle it here? Okay. Yeah, almost that way. So the trick here is we reconstruct our open set. Trick here is 啊，对，谁跟谁是 disjoint？不一定啊，我没有 put 这个 condition 进来，然后不对啊，对，没有错，就是这个原因。Yes，就是这个原因。你家肯定比你大嘛，对不对？啊啊，对，没有错，在这个里，对不对？呀，嗯呀，更大个，yes，可能更大个，可能呀。Okay, so we have to deal with this kind of situation here. So the trick here is to reconstruct our open set. So we will take UN prime to be UN, take away the union of the closure, okay, of your neighbor's house. Okay, 你墙壁我都不要动到。Okay, your closure 我都不要动到。Okay, closure of WI from 1 to N, the previous N one. Okay, and similarly we did it for W. Okay? Similarly we did it for W. Okay, so um, should I show you how it works first, or should I show you why it works? What do you prefer? Why first, and then see how it works. Okay, good. This is my logic. Okay, so let's see why it works first. So for this to work for sure, you still need to keep your openness first, right? And then you sure need to be able to cover the thing that you want. Okay, so there are these two things to check here. So first, check that this UN prime is open first. Okay, so check that this UN prime is open. So how to check? Is it open or not? What do you think? If it is open, why is it open? Yes, closure is closed, then you are taking a complement of a closure. Yes, finite union. Finite union, okay, yeah, finite union. Yeah, closure, you need finite union to be closed. Okay. So because it is the difference of a open set and a closed set. Okay, so still open. Yeah, so you can think that this is the same reason why W prime is open. Okay. So do So the next question is, does this UN prime covers A or not? Does it cover A or not? So for every point is in A, should it be in some UN and then not in the closure of X of WI? So one part is easy, right? So my claim is UN prime covers A. So one part is easy. So which part? So for every point in A, of course X is in UN for some UN. This is how we constructed it. But is it true that it is not in WI bar for OI? Why? What happens if X is in WI bar? Huh? X of course cannot be in WI anymore, right? Because intersection is empty. So only where that you can stay in WI bar is your point is the limit point of your WI. But but it cannot be true. Right now. Have an open set around your X that's separate. Separate who? A and B is enough? Enough? Is enough? We choose WN bar to be intersection. Well, let me check. I think we have stronger thingy here. Let me check. We have a stronger thing. Maybe I copy something wrong, is it? Oh, I think we have stronger stuff. We have W N bar intersect A is empty. Okay, yeah, we have stronger statement. Yeah, okay, I think that's good. Okay. Right. And then so similarly, same way. So I'll write here since WI bar intersect A is empty. So similarly, this is true for Vn. Okay. Okay. So these are open set, we cover, and then last thing we want to show is we want to show that lastly we want to show that U prime are taking the union of all UN prime and union of all U prime is empty. Is empty. Okay, is it empty or not? So without loss of generality, okay. So suppose X is in some intersection of U I prime and WK prime. So without loss of generality, we assume J less than or equal to K. Okay. Then what this means is X is in UJ and X is in WK prime. Can this be true or not? Can this be true or not? Huh? Why? What is WK prime just now? We take WK, take away union of 1 up to K of U I R. Okay. So because J is less than or equal to K, right? So you have already taken away some of the of UJ already. Okay. So X cannot be in UJ. Okay, contradiction. Okay, so how this works, actually, how this works. Let me give you a scenario. Can you read what this theorem is, this construction is doing or not? Let me give you a scenario here. Okay, let me give you a scenario. See what is this set is doing. Okay, let me give you a scenario. Very similar one in the book. Do this. Let's see this diagram here. Yeah. So it's a rectangle. So where is A? Where is B here? So let's call the first one A, and then the second one B. Okay. And then the green one is what our U1, UIB, and then the yellow one is our VN. My V and U looks the same. Let's change a bit. Okay. Okay. So let's see what this construction is doing here. So let's copy paste here. Too big. When I size. I have to keep the original one in case later we make some mistake. We know how to revive it. Which one? Oh, okay. Huh? Which one? Oh, W, huh? Anyway. Oh, which W here? Huh? Okay, okay, okay. Thank you. I'll change it. Okay. So let's see. Yeah. Oh, intercept too much, huh? Okay. Take away a bit. Too much, too much. Sorry, yeah. Too much. Too much. Take away a bit. Thank you, thank you. Okay, too much. Okay, let's start now. Okay, I need to change this one also. Wait, too much. Okay, how about I just read this one? Copy it. Okay, so let's write down what's the formula for U1 prime. U1 prime is equals to U1 take away W1 up. Correct? U2 prime, U2 take away U1 bar take away U2 bar. Okay, U2 bar, W2 bar. Sorry. Yeah, okay, good. So let's see. What is U1? What's the new U1 bar now? What do you reckon? What do you reckon? What's the new U1 bar? So you need to look for two things, right? What's the two things you need to look for to find U1 bar? What's the two things you need to look for? Say it. Say it. What do you need to look for if you want to find U1 bar? 不知道？你那边有等于，找一找 U1 bar 等于什么？讲啊，U1 minus W1 bar. So you need to look for U1. Where is U1? The top green guy. W1 bar, the closure of W1. Okay, so where's the closure of W1? The problem here is closure of this open set is what? You need to include the boundary here. Okay, so this W1 here, you need to remove everything in this closure. Okay, so you need to modify this bit here. What's this bit here? So you need to modify this bit here. Okay, cannot stay inside the boundary of W1. So you need to stay away from it. So let's stay away from it. Stay away, away from it. Like this. Okay. But you can see there's some problem here. Seems like this U1 still have some intersection with other W. But in our proof, right, we say what? There shouldn't be intersection, right? Okay, so let's continue what this construction is doing. Okay, let's continue what this construction is doing. How about U1 prime here? U1 prime here, what do you need to do? You need to take away all the previous WI closure. Okay, so from this case here, there's no intersection between U2 and closure of W1. But there's an intersection with the closure of W2. So you have to remove this part here. Okay, so let's remove it. We need to avoid touching W2 bar. Okay, but as you can see here, the new U1, the U2 prime, still have intersection with the old W1, W2, W3, right? Okay, so let's see what happened to the W part. Okay, what are the W prime? Okay. So similarly for W1, what do? You take W1, take away U1 bar. Okay, take away the U1 bar. So you take the WI, take away the U1 bar here. So what you get? Okay, so can we just keep this picture like this for now? Okay, I think we shouldn't do it. So let's do it properly. So we will change my W1 bar to something else. Okay, take away the previous U1 bar. How about U2, W2, right? W2 here, so if you refer to the original picture here, you need to take away U1 bar and U2 bar. Does it make sense? Yeah. So let's do it. Good. So the picture should look something like. How about W3? W3, you need to take away all the previous closure. So it's something like. No, should be no intersection. Okay. So in this way, you can miss out all the intersection. Does it make sense? Yeah. How about I make this one cleaner a bit? Okay. Yeah. Okay. So far, okay. Any question before we take a break? So later, the theorem we're gonna prove is called the Uryshon metrization lemma. Sorry, not lemma anymore. It's a theorem saying that every second countable regular space is metrizable. Okay. Yeah. So this tells us when you can put matrix on the space. We can take a break to talk about this theorem. So let's take a break about U1203. I don't know. There's one way I think about this theorem. It's like you see, for example, back home and when Chuan now, you still got space between you two, right? So somehow I can give a distance saying that oh, this is the distance between two of you. But let's say there's a swarm of people moving. Then the distance between you and when Chuan is getting smaller. Can it be smaller until a stage that it is indistinguishable or not? Does the cardinality of the set affect the distance? But here, what's this theorem characterizing is if you got so many people, but you are second countable and you are regular, then I can put matrix on it. I can give distance. There's no cardinality here. But how I control this cardinality, I have this countable basis to cover them. So somehow you use basis to after you group them, you know how to separate a closed thing in the point. Then with this characterization, somehow you can define the distance on it. So what is distance in this case? What is distance in this case? What does distance do actually? If the distance is positive, then somehow you can separate two things. One is in particular. But the property given in here is you only know how to separate closed set and the point. Then with this second countable, you can improve it into separating two points. The point of this theorem here. Yeah. Yeah. 很大什么？哦，okay. Start. Maybe we'll try to skip some detail of this proof here, but focusing on how this proof is constructed. Again, because this proof is also very technical here. So instead of defining a metric, right, we won't do that. What we're gonna do is we will show that this space X is homeomorphic to a subspace of the infinite product. Okay. So infinite product of R, we have a product topology on there. And what we didn't mention is if you check out Theorem 20.5 in Moncrief, or maybe I'll put in tutorial, that the product topology on infinite product of R is induced by a metric. Okay. It's induced by a metric. This metric is kind of tricky. It's defined as this supremum of the minimum of the difference between each coordinate and 1. Okay. If it's larger than 1, we just take 1 divided by. So the I is the coordinate. Okay. Okay. So you have you are homeomorphic to a subspace that has metric. And so you can use the metric A to induce a metric on your second countable regular space. Does it make sense? Okay. Okay. So now I'll go change to build a homeomorphism to a subspace. So if you have a homeomorphism, okay, to a subspace here. So what do we want to do here actually? So what we want to do is we want to build an injective continuous map into this infinite product. And I want to show that it is homeomorphic on its image. Okay. So I'm gonna build. So I'm going to build an injective continuous map. Okay. From X to the infinite product such that X is homeomorphic to its image. Do you guys think it's very unnecessary to say that X is homeomorphic to Fx or not? If I already have an injective continuous map, do you think it's unnecessary? What is homeomorphic? And then what else? Adjunctive continuous, inverse also continuous. So already injective, already continuous. So surjective or not? Subject to what? To the image. Function is always subject on the image, right? Because by definition. But inverse continuous or not? Might not be. Okay, so you need to define one that works. Okay, so let's see how we define this capital F here. So you want to define something into countably many things. Okay, let's see what is the countably many things we're going to produce here. Right. So step 1. What we're going to do, what we were showing is we will show that there exists a countable collection of continuous function Fn from x to 0, 1 having the property that for all points in x and for all open U containing x, so it's an open neighborhood of x, such that there exists an n in n, so there's some function in the sequence that can differentiate x naught and the complement of open set. Hey, you might think that this is huge, huh? Don't you think this is huge? It has to work for all point x and all open set. But I claim that I want to find a countable collection of this function that can all open set. Points can already be uncountable. What's more, the open set. Maybe parallel. So, how to do here? But at least you need to get some function up first. What kind of function can separate separate points and close set, because this is open complement of open set. So when can you get the separation? This kind of function. Let's get the function first and then we see if we can reduce it or not. How do we gain this function here? What kind of, where can we obtain this kind of separation function that separate points and close set? Uryshon lemma. Okay, but how to use Uryshon lemma? What does the space have to satisfy? S has to be normal, but we have X is second countable regular. Is it normal? Why? This, we just prove it, right? So by the previous theorem, we know that. So by previous theorem, we know that second countable regular implies normal, but normal implies we can separate. So we have a function, continuous function, such that given x naught in x and u in x naught, that f and x naught greater equal to 1 and f u c equals to 0, for example. Okay. U contain x naught. U contain x naught. Okay. Okay. Okay, so this part here is by the Uryshon lemma. Okay, but like what we said just now, if you pick for all these choices, maybe you get more than countable. But what we're gonna do now is we induce the second countable properties in. Okay, so now let Bn be a countable basis for x. Okay, and we can just look at these two set here, which is Bn bar living in B bar. Okay. we can look at this kind of pair. Okay, for this kind of pair, what do we have? For this kind of pair, we can find G and M. Okay, in X01 such that G and M of Bn is 1 and the complement of Bm is 0. Okay. For this kind of pair, you can find the separation function here. Okay. The claim here is this is the countable collection you want. Okay. So first of all, it's countable, right? Cross n should be countable. Okay, because m is countable, n is countable. If you consider these two pair give you one new thing, so n cross n is also countable. Okay, so the problem is, does this do the job for every point and every open neighborhood containing that point? Okay, so this is the thing you need to check. Yeah. If it exists, if it doesn't exist, if it doesn't exist, it will be a problem. Should it always exist? I think it should exist. Should exist. Later, I think in this proof you will see how this thing get used, and then it should exist. Okay, should exist. Okay, you can see the proof later. Okay, we will see how they get slipped into each other. Okay, then you will see that it exists by the basis property. Okay, so the claim is the collection G and M is the required collection. Required countable collection. So countable is obvious, so we just need to check whether it can separate all points and all open set. So proof of claim. Countability is obvious. So now take any point, okay, any point x0 and any open set containing x0. Okay, what one can do is because we have a basis, right? So one can choose Bm, okay, such that S0 is in Bm and Bn is living in U. Okay. But what? But using regularity, okay, we can find a smaller open set such that the closure is living inside. And the closure is living inside where? Living inside. Yeah. Okay. But what? Hey, here. Huh? Here. So what can you do? You got a new open set again. Play your basis business. So there exists an n such that Bn living inside V. So since Bn is in V, obviously Bn bar should be living in V bar. And then V bar is in Bn. Okay. So then you can use just G and M to separate the two things. Okay, you just use G and M to separate the S0 and vanishes outside Bm. In particular, U. Okay, in particular U. Does it make sense? Okay. Follow? Any question? No question? No. But you pick Bn from the same set. The choice of Bn is countable. So how do I pick this G and M? I just pick based on Bn and Bn. So if you go through any other choice, the choice of Bn and Bn, where do you make the choice? From the countable collection of B. Does that make sense? So it's the same G and M that you have defined before. So you are reusing these G and M. Even if you change point, change open set, but who are the bases living inside this open set? It's the countable collection, right? Yeah. Okay, or not? Understand? Understand? No matter what point you pick, the basis you have is just countable. So you get squeezed between two countable things. So you have at most countable, cross-countable function. Okay or not? Does it make sense? Yeah. Okay. So now we have these countable things, right? How are we gonna build this map? This is a very genius map. I think you should appreciate this because later we will use it. We'll see this kind of map again. And maybe it's very useful in functional analysis as well. Okay, so what this map here is, I send a point to the collection of countable function that evaluate at this point. So what do I do here? I change the space, topological space, into a bunch of number. And then this bunch of number is living inside another topological space. Yeah. Okay. 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 Right. So what do you do next? I think we won't check it now. So let me ask you what we need to check until this stage. If we're gonna show that this F is homeomorphic to its range, to its range. What do we need to show? Okay, first you need to show that this is injective, right? And this is continuous. And then F subject on image is pretty obvious. So next is F inverse is continuous on Fx. Okay. Yeah. Does it make sense? Okay. No? Yeah. So I put the details in my notes so you can check it out. So in particular, these three cases characterize something what we call an embedding of a topological space. Okay. So this characterize something we call embedding. So if you look at Moncrief, they put embedding. Okay, maybe I like embedding more, so I put embedding. Other book also put embedding, so they are the same if you like. Okay, but for my convention, we'll say that a map F from a topological space to the other topological space is an embedding. Okay, embedding if F is an injective, okay, continuous map such that it is a homeomorphism. Okay, onto its image. I suggest you to think about this embedding as a embedding in your differential geometry. Do you have embedding or not? I think differential geometry got a few words, right? Embedding, submission, immersion, didn't learn. No, didn't learn. Like, I thought that one is a very crucial thing. No, man. Inverse function theorem, the main two. Don't have that. So weird one. Immersion, submersion don't have. Embedding don't have. When I first learned those courses, these are the three words that I'm super confused. So that they have characterization on the tangent space. You guys learn tangent space, tangent space of what? Yeah. So tangent space of who? Curve. Curve plane. It's basically differential manifold. Okay. That's fine then. But it's a very related concept. Because in differential geometry you can do more precise thing because there's a atlas. You guys learn atlas or not? How can you guys learn atlas? Because only in R3. Surface, parametrization of surface. No? What atlas you learn? Okay. You explain one example. Hmm. Okay. So it's like actually it's parametrization. Okay. Yeah. Okay. 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 Okay, good. Right. So um so this is the proof of Uryshon metrization theorem here. So in this proof, what we can see is you can mm, so you can see that what's the where's the range of our map? Our map is from 0 to 1. So again 0 to 1. So in fact, we don't just map into infinite product of R. Actually, we map into infinite product of 0 to 1. Okay. But to deal with some technicality problem there, we somehow need to change the topology, product topology there. And then we somehow need to do some adjustment to Fn. If you like, you can look at Macris. But what's the point here is really we can just map into this compact set. Oh, I haven't teach you why infinite product is compact, right? Infinite product of compact space is compact. That's the Tikhonov theorem. Okay, we will see it soon. Okay, and Hausdorff property is product different. Okay, so that one should be easy to see. And after this, theorem here, I think I set a assignment question on this theorem, which is called the Higgs extension theorem. So we can use Uryshon metrization theorem to prove this Higgs extension theorem. So what's this? What's the content of this extension theorem? So let X be a normal space again, okay? And then let A be a closed set, closed subset. Okay, be a Okay, the content here is any continuous map of A into a closed interval can be extended to a continuous map of all x. Okay, similarly into AB. And the second statement is if you have a continuous map into R, okay, then you also can extend it to a map into R. So what's the difference between these two statements? What's the difference between closed interval and R? Sorry? Bounded, one the other not bounded. More? What's more? Okay, one is compared, the other is not. One is closed, the other is open. Okay. So these two somehow encapsulate all the possible cases. Okay, possible cases for your full domain in R. So why we place A before B? Because we can prove A first and then we can modify proof of A into proof of B. Okay. So we can focus on proving A first. So what's the significance of this theorem here? What's the significance of the theorem here? So like if you have a function on R, say this is the closed set you have, okay? The problem is, can you extend this function or not? Okay, to a continuous one. Does it make sense? When can you extend it? Okay. When can you extend it? Okay, so this, it turns out this could be a quite hard problem here. So, so we have this T's extension theorem. How about complex? Complex analysis, do you guys learn extension function or not? Extending function? Extend to an entire function? No way. Why you guys don't learn? They learn one. They only have 2 weeks to finish the complex analysis. Why you guys don't learn? They learn. Yeah, so that's the problem with SMUM here. Complain. You guys should complain. Because the level different too much. Differ a bit is okay. Too much. Very important stuff don't teach. You should complain. Student council, do the works. Complain. You cannot ask them to feel, because they don't know what happened. So you guys have to engage all the mathematics students, engage, talk to them. 跟他们聊天，你们课做了什么？跟全部聊天，你不能叫他给 feedback。他是新人，他不知道什么该学，什么不该学，知道吗？跟他们聊天，去找每一个 batch 的人，跟他们聊天，跟 Peter complain。OK， yeah。OK 啊 ，All right. So we're not gonna prove this because this proof is quite MA proof. You will use a sequence of function and then you use the Weierstrass M test to prove it. Okay. You can check. You can check out the Moncrief proof, or I put out a proof sketch inside my lecture notes so that it can help you to understand. Okay, what's the actual proof doing? Okay, and we still got time. Maybe we can go a little bit further. There are two metrization theorem that we're not going to prove. It's this two. So this two is not going to prove, but it's worth mentioning. Okay. Hey, by the way, you see me like skipping a lot of proof here. So our test won't include at least from Higgs extension theorem onward. Okay, we won't include inside the test. All right. So this now the last one I mentioned here. After this, I think we won't include into the test. Okay, but we will still do it for the completeness for this course. Okay, in future you need to use because what we're gonna establish later is very useful for other courses or your future. Okay, but for exam purpose, so you need to split these two up. You need to study for exam, you need to study for yourself. These two things. You cannot just study for exam. It's not enough. Okay, because life still go on after exam. So after life, what you do? You just study for exam. Kosong you are kosong. 什么是 kosong? Zero 啦，空空。Okay, you go out with 空空。Okay, so there are two statements not going to pursue but worth mentioning. Okay, so the first theorem is called the hey, did I copy the name wrong? Nagota or Nagata? Nagota. Nagata. Okay, seriously, Nagata. Okay, Nagata-Smirnov metrization theorem. Nagata should be a Japanese. Okay, so just now we just give a sufficient condition for metrization, but these two theorems tell us the necessary and sufficient condition. So a space is metrizable if and only if S is regular. Not enough, of course. And what's the thing we need to control just now? We control how to separate. The other thing we need to control is basis. So what kind of a condition on basis now? Has a basis that is countably local finite. Okay, we haven't touched this concept yet. So what is locally countably finite here? Okay. So moreover, regular here, just now what do we have? Second countable and what? Second countable and regular, right? Okay. So now if they add in this condition here, second countable change to countably locally finite, then got if and only if statement now. Okay. So what's this countably locally finite doing? So you need to split into two. We need to define what is locally finite first. Again, then we define what is countably locally finite. So we briefly run through this concept. See if you can imagine what we define. So a collection A of subset topological space is said to be locally finite in X. Okay, in X, if for every point in X, okay, there exists an open U containing X such that U intercept only. Want to guess what is this? Intercept only what? Then you fill in the blank. There's something I haven't used in the word, I haven't used in the definition, right? Finite. So finite have to come in here. So intercept only finitely many what thing? What point? Elements of A. Okay. So you have a collection of things such that at every point in your X, you have a neighborhood that only intersect finitely many of your element in your A. Can you imagine or not? Imagine. Just imagine first without example. Imagine or not? You see, intercept elements of A is a subset, right? So when we say intercepts, set and set intercept, meaning they have non-empty intersection. Do you remember? Yeah. If I say A and B intercept, their intersection is non-empty. So what's wrong with that? Next one. Subset ma? Is a set ma? I take U is a set ma? Set intercept is what? Intersection is non-empty. Okay, if the intersection is uh, empty, then they don't intercept. Okay or not? So meaning there's only finitely many subset that have non-empty intersection with the open neighborhood U. Okay, does that make sense? Okay, can you imagine or not? After you imagine, maybe you can challenge yourself if you can give an example or not. I think example should be quite straightforward. Go to R. Let's try go to R. Okay, so how about countably locally finite? Okay, how about countably locally finite? Okay, so also a collection of subset. So it's said to be countably locally finite. So this countable need to come in. So how do we put this countable in? So let's see. Locally finite if my collection of A can be written as the countable of locally finite collections. Maybe we denote it as A. Okay. So they are countably union of collection. Okay. Quite big. It's quite big. Okay. It's quite big. Okay. Countably union. So you have the previous collection already, right? Then you take countably union of them. They're quite big. So not as small. And that's why we can go backward, go forward between metrization and this. Okay. And then the second metrization theorem is by the Smirnov. Okay, so the same guy just now. A space is metrizable if and only if it is a paracompact. Okay, I'm not sure if you heard this before. Paracompact, Hausdorff. Okay, paracompact, Hausdorff. So somehow, how much thing we have talked about? This one separate already, know how to separate 2 points. And then paracompact maybe is something about compactness, about open cover. But we haven't touched basis yet, right? Okay, so instead of talking about basis, we will say that this space is locally metrizable. Okay, so there are two new concepts here. Okay, so there are two new concepts here. So let's briefly say what's the two new concept here. So what is paracompact is? So this word, this name bears compact inside the subword, right? So we have to talk about something about the open covering. Okay, so if every open covering A of X has a locally finite refinement. Okay, refinement B that cover X. Okay, so can you imagine what this is doing or not? What is refinement? Okay, you can think of the refinement in your Riemann sum, upper sum, lower sum, or what sort, whatever. So it's the subset. Okay, you can find a subset of these element of open cover. And then what does this subset of open cover do? They are locally finite. So I have to do what we did just now. So what's the collection of set that is locally finite? For every point in your space that exists a neighborhood of X such that it just intersects finitely with this. Okay, it's finitely with this collection. Refinement. So refinement here says what? It might not be the element from A. Might not be element from A. Maybe it's just a subset of the element from A. It's fine. Okay, refinement here. Okay. If they can do the locally finite job, then good. I call this space a Parham space. Okay or no? Okay. And what's locally metrizable here? So you see local again. So must be local down to a point maybe. Okay. So we'll say that a space is locally metrizable if for every point in X, okay, it has a neighborhood. It has a neighborhood U, okay, that is metrizable in what topology? What do you think? In the subspace topology. Okay. So if you have space, you have a neighborhood. So you just look because it's a subspace of the metric space. You look at the subspace topology. So if I want to metrizable in the subspace topology means what? I need to have a metric on this neighborhood that induce the subspace topology. So if you put all these adjectives together, I means what? Means what? You want to put all these adjectives together means what? If your space, you can put metric on it. What does it mean? If you have open cover, okay, on your space, you can look at the refinement. If you have a refinement that is locally finite, such that every point have a neighborhood that intersect finitely many elements with this refinement, and also every point has a neighborhood that is metrizable. What is refinement? So, so A is a refinement of B if for every set in A is a subset of B. Yes, I think this one. And is a refinement of B if for every set in A is a subset of B. I think that's right. Union of A. Do you want the union to hold true? Yes. Can. Yeah. Okay. Cut it smaller and then the union is the same. Can. Yeah. Yeah. Makes sense. Yeah. Can. Sure. 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 So some useless. You could happen. Could happen. Could happen. Yeah. Could happen. Might not be always true, but could happen. Yeah. Could happen. Yeah. Okay. Not just refinement, or those refinement need to do this locally finite business. Somehow meaning what? Meaning you okay, so meaning you have a neighborhood that's metrizable already. So that neighborhood you can give some distance. And then you try to piece this distance together, right? So this piecing of this distance together, somehow I think you need to use parallel compact because you have finite intersection with other thing inside B. So you can use this finite intersection to connect your distance. Because in the end, your metric should be continuous. Right? Yeah. That's property of metric. No, not really. Yeah, I mean, sure. So somehow you need to use the intersection. But I mean, these two topic right is treated quite formally in Macris. So if you are interested, we won't touch it. Yeah. Why metric is not continuous? Is metric always continuous or not? Okay. Yeah. So I mean, if you want to have a formal treatment on this tool, you can look at Macris. Okay, but we won't pursue. But just give you this idea. Yeah, well, things can go really crazy, a bit crazy. Okay, because yeah. So this is how we do maths. No? So we go step by step, step by step. Then we go how to say how to say 仔细 how to say more details. Yeah, sure, more details. Yeah, going details, more details. Yeah. Because you can see this is if and only if, right? So you can straight away jump from regular countably local finite to this parallel compact and locally metrizable thing. So you can do that way. Okay, ignore the metrizable. So these four concepts are somehow equivalent when you pair them correctly. Make sense? Okay, if makes sense. So there are three last very important thing we're gonna do in next 2 weeks is one is Tikhonov theorem, and then second is Stone-Check compactification, and then lastly we'll do a Ascoli theorem. Okay, yeah, very big theorem, very important concept in the frontier of research. Yeah, they answer very important question. For example, how you extend the function. Just now we met already. One of them is the Tick's extension theorem. Okay, in fact, it's quite hard to do. You need the Uryshon metrization lemma and metrization theorem. Okay, yeah. Huh? Make sense? Okay, so if you are concerned about exam, I think exam content will be up to like what you had in your assignment. That's all. Okay, after Tick's extension, don't have. Okay, so in the exam, please, you need to uh, internalize. Okay, I don't want to use memorize. Okay, internalize the definition. Okay, so because there's no definition given. Okay, because if I give definition, almost the answer is drop out already. So if you don't know the definition, if you just memorize, you don't know how to use, I give you also no use. Okay, so you need to internalize the definition. Okay, all these concepts is clicked together one. So you should be able to form a storyline. 知道怎样理解吗？怎样知道你读会吗？怎样 check？我给你一个方法 check 要不要？怎样代表你读的会？不要带着书去跟别人讲，看他听得懂你在讲什么，明白吗？就跟你从你旁边那个开始聊先，另外一个学过的听得懂你在讲什么，然后你再去跟没有学过的看他听得懂你讲什么，这样子 train 哦。Okay, it's not just by reading. You need to communicate with each other. Check. OK? 可以吗 ？Understand 吗？可以明白吗？对啊，你一直读没有什么用。OK，当你开始讲的时候，你就会开始想啊。OK? Yeah. All right. So we'll see you next week.